see. Okay, so today we're going to just do a little bit more review with multiplication. Well, actually, we're going to spend time with multiplication. I want to go back to page 8, do that problem at the number 7, that word problem that we have there, and also want to make sure that you guys saw that link for 5.02b. And we're going to do a practice worksheet today with multiplication. So let me find that link again and put it in the chat box so you guys can print that out if you're able to. All right, so let's go in your packet to number 7. Okay, so page 8. We did number 6 in class, at the end of class, and let's try number 7 here. Okay. Different point values are awarded for different shots in basketball. Use the information to determine the total points scored by each player. We have a 3x3 matrix showing and a 3x1 matrix. All right, so Ray, Chris, and Jerry, we see their total number of free throws, 2-pointers, and 3-pointers that are made over the collection period. Right. But we also know that in terms of the connection between the different types of shots and points, right, we can see 1, 2, and 3. 1 for free throw, 2 for 2-pointer, 2-pointer, and 3 for 3-pointer. Okay, but let's see if we can kind of match up the matrices here. So this is a 3x3 matrix. And this second matrix is a 3x1 matrix. Okay, we get the 3's to match up. So we know that the multiplication is possible, but we know that our resulting matrix is going to be a 3x1. Okay. Notice that in this 3x3 matrix and 3x1 matrix, not only are the inner dimensions matching, but they're also, in terms of the numerically, but they're also matching in category. So that's important for word problems as well. That's a way to kind of ensure that we are on the right path, because the column for the first matrix, the categories are free throw, 2-pointer, and 3-pointer. The 3 rows of your second matrix are also the same categories, right? Free throws, 2-pointers, and 3-pointers. So these are the dimensions that are going to kind of combine and kind of merge to allow for a 3x1 matrix to appear, which will show the connection between the names of each player and how many points they're scored, right? But along the way, this information is getting merged to allow for that connection to be made. Okay, so what we're left with is a 3x1 matrix. So I'm not going to have enough room to show all the, to have the, well, I guess maybe we can use number 5 to show that, or the space for a number 5 to show that. But we have Ray, Chris, and Jerry. And we're going to be ending up with a 3x1 matrix. Points is what we're going to be concerned with, right? Okay, so we're going to be matching the row with the column. So if you want to have it kind of lined up the way that we have it here, you can put that over here. Okay, 3x3 matrix with 3x1 matrix. We're going to end up with a 3x1 matrix. So first row with first column. So 44 times 1, 32 times 2, and 25 times 3. Okay, for Chris, 37 times 1, 24 times 2, 31 times 3, right? 37, 3 throws, 1 point each, 24 2-pointers, 2 point each, 31 3-pointers, 3 points each. So we're trying to total up the number of points scored by each player. Okay, third row, first column. Okay, we total all this up together. Ray ends up with 183 points. Chris, 178. And Jerry, 200. Questions? Okay, so in the remind message, as well as in that meeting chat box, I included a link to today's worksheet. Okay, so we'll work through a part of it because the second part, back page, deals with inverse. So when we get through to number 9, then we'll do an intro into inverses with tomorrow's section, and then we can kind of come back to number 10 and 11. And it's also good that we're able to get a head start into tomorrow, because tomorrow is kind of a little bit like 2 sections, and I want to kind of, once we're comfortable with multiplication, let's start inverses. That way we can get through all the material, and then we can save Monday and Tuesday for review, and then quiz on Wednesday. Okay, so number 1, 2, and 3, we're just determining the dimensions. We're not finding the, we're not actually multiplying, just to kind of show that we understand if and how matrices multiply together, and also what the new dimensions will be. All right, so number 1, matrix A, let's find the dimension for matrix A. Rows followed by columns. Row goes from left to right, columns goes vertically. So we have 2 rows and 3 columns. So a 2 by 3 matrix. Okay. Matrix B, 3 rows and 1 column, 3 by 1. Okay. If you want to put them side by side to see whether the inner dimensions match, you have a 2 by 3 matrix trying to be multiplied with a 3 by 1 matrix. Right, the inner dimensions, they do match. Column of the first matrix must match the row of the second matrix. And because they do match, we know our resulting matrix is going to be a 2 by 1. All right, any questions there? All right, go ahead and try 2 and 3, and we'll compare our answers. Okay, matrix A, 3 by 2, 3 rows, 2 columns. Matrix B, 3 by 1. It's not going to quite line up, right? We don't really care that the rows are matching. We need the column of the first must match the row of the second. They don't match. Therefore, we're not going to be able to multiply those together. Okay, not possible. All right, try number 3. Right, matrix A, 3 rows, 1 column. One row, 3 columns. Okay, it does pass the test. Our inner dimensions are the same. So our resulting matrix will just be a 3 by 3. All right, so now number 4, the rest now we're going to go and actually find, multiply the matrices if possible. Okay, so number 4, let's find the dimensions first. 2 by 2 with a 2 by 1. Inner dimensions match. We know that our resulting matrix will be a 2 by 1. Let's go ahead and get the matrices set up so that it's easy to see how these numbers will combine. Okay, the row of the first matrix is going to pair with the column of the second matrix. We're going to end up with a 2 by 1 matrix. This is a 2 by 1 matrix. This is 2 rows and 1 column. Right? So we're just going to pair the numbers, go from left to right on the first matrix and going to go top to bottom on the second matrix. We're just going to pair each of them with a partner here. So -6 times -1. And then add with the next term. Okay, now we're done with this. Move on to the next term. -2 goes with -6. Okay, next up, second row, first column, -4 with -1. Plus 3 times -6. Okay, so 6 plus 12, 18. And 4 minus 18, -14. All right, any questions here with number 4? All right, try number 5. Okay, 2 by 2 with a 2 by 2. Inner dimensions match. We're going to end up with a 2 by 2 matrix as well. Right, any questions with 5? All right, if no questions, try number 6. Number 6, we have a 2 by 3 matrix paired with a 3 by 1 matrix. Inner dimensions, they do match. And we're going to end up with a 2 by 1 matrix. Okay, check your answers. And let me know if there's any parts that you want me to go over or clarify, or if something doesn't quite make sense.
Can you go over 6 again?
Yeah, number 6. So we have a 2 by 3 and a 3 by 1. Okay. We know we're going to end up with a 2 by 1. So here, this is a 2 by 1 matrix. I use that line here to kind of show the matrices that are in play. And now, to fill in the spaces, we're going to go from left to right on the first matrix and go top to bottom on the second matrix. Okay, and we're going to pair up each of the numbers. So 1 goes with -3, so 1 times -3, plus, move on to the next number, 4 times 4, plus 2 times -1. So -3 plus 16 is 13. 13 minus 2 is 11.
Oh, okay. All right, I got you. Thank you.
And then these numbers also same idea. Go from left to right. This is second row, first column. -1 with -3, 3 with 4, and -4 with -1. Okay, any questions? Any other questions? All right, try number 7. All right, what do you guys notice about number 7? Are we going to run into any issue if we were trying to multiply those together? So not possible, right? We have a 3 by 2 matrix trying to multiply with a 3 by 2 matrix. If the inside dimensions are not the same, we're not going to be able to pair them up and create a multiplied matrix. So number 7, we just have to stop and say that it's not possible. Okay. All right, back page. Let's go to number 8. Okay, 3x2 matrix with a 2x2 matrix. Okay, we're going to end up with a 3x2 matrix, 3 rows, 2 columns. Move from left to right on each for the first matrix and go top to bottom on the second matrix. Okay, so this space is first row, first column. So we're going to look at first row and first column to get these numbers to show up. So -3 times 0 plus -1 times 6. Okay, second row, first column, 0 times 0 plus -6 times -1 times 6. Okay, -4 times 0 and 2 times 6. Okay. This empty space here is first row, second column. Okay, here's the resulting matrix. 0 and -6 is -6. All right, any questions with 8? Okay, number 9 is a bit of a longer problem because we have 2 sets of multiplications going on. But you see there's a set of parentheses here which tells us that we're going to have to resolve this first. Okay, so we're going to multiply this first. Okay, and then once we get this resolved, then once we get this matrix to show what it's once we get this to be a new matrix, then we can worry about how to multiply with this 2x1 matrix. Sorry, this 1x2 matrix. Okay, so let's deal with this first. Okay, inside dimensions match. We know we're going to end up with a 2 by 3 matrix. Okay, so I'm ignoring this first matrix. I'm just going to focus on solving my first issue here. Okay, we know we're going to end up with a 2 by 3 matrix, 2 rows and 3 columns. Okay, so to fill in the first row, first column, we'll look at the 4, -1, and the 0, 0. So pair up each number and move on to the next number. Okay, first row, second column. Second row, second column. All right, first row, third column. Okay, second row, third column. Okay, let's get that resulting matrix. This is 0, this is 0. 8 minus 5 is 3. -10 minus 30 is -40. Okay, 0 minus 5. And 0 minus 30. Okay, so we solved the first issue, right? Trying to get this down to one matrix. So let's do our second part of the problem, which is multiplying this -5, 1 with this new matrix. So here we have a 1 by 2 matrix trying to get multiplied to a 2 by 3. Okay, 1 by 2, 1 row, 2 columns, 2 rows, 3 columns. Okay, again, we go through our check. Our inner dimensions, they do match. So we know we're going to end up with a 1 by 3 matrix. Okay, let's set up our multiplication again. Okay, I like to space out my second matrix so I can give myself room to add all those terms together. Okay, 1 row, 3 columns. Okay, first row, first column. I'm looking at the negative 5, 1 and the 0, 0. First row, second column, negative 5 and 3, 1 and negative 40. First row, third column. We know we're ending up with a 1 by 3 matrix, so here's our resulting matrix after multiple steps here. This ends up giving us 0, negative 15 minus 40, and then 25 minus 30. Any questions? Okay, so before we get to 10 and 11, these are dealing with inverses. I want to introduce the topic of inverses before we're able to do these problems. But yeah, number 9 is a bit messy because we have to go through multiple steps. So any questions with number 9 before we move on to inverse notes? All right, so if you guys can go to page 9 in your packet. So when we talk about inverses, it's basically reciprocals in terms of multiplication. Okay, so if we have the inverse of 2, which is really 1/2, and the special relationship between something and its inverse, between an expression or value and its inverse, is that they have a kind of way of canceling each other out, right? 2 times 1/2 gives us what? Just 1, right? 2's cancel out. 3 times its inverse also kind of have a way of undoing and canceling each other out. Okay, 3 times 1/3 is 1. 25 times 1 over 25 is also 1. So in a way, this is also connected with the idea with matrices and its inverse. A matrix inverse, if I were to multiply a matrix and its inverse, just like if I were to multiply a number and its inverse, they're going to kind of cancel each other out, okay? And what we have is we're going to get something called an identity matrix. An identity matrix is kind of like a matrix version of 1. Okay. So if I were to multiply matrix A and matrix B, if matrix A and matrix B are truly inverses of each other, then they will produce an inverse matrix. Sorry, identity matrix. Okay. Basically, a matrix version of 1. And I'll show you in a second what the matrix version of 1 looks like. But if it's a true identity, if it's a true inverse, that means I can also flip the order and I'll also get the same thing, right? Normally, when we change the order of multiplying matrices, we're not going to get the same result. But if we're dealing with if these are truly inverses of each other, we will get it both ways. Okay, so an identity matrix is going to look different depending on what the dimensions are. So here is what identity matrix definition is. It's a square matrix with diagonal elements of 1 and all the elements of 0. So if there's only one element, if it's just a 1-by-1 matrix, then it's just going to be 1. It's going to look just like how we would see with other numbers. But if it's a 2-by-2 matrix, your identity matrix will always look like this. This is basically the matrix version of 1. Okay, your diagonals will be 1, but everything else will be 0. If I have a 3-by-3 matrix, then an identity matrix would be very similar. It'll be 3-by-3, but then the diagonal, the diagonal from left to right going down are going to be 1s. And all the other numbers will be 0. So this is basically a 3-by-3 matrix version of 1. Hey, if I want to find a 4-by-4 identity matrix, it'll look like this. The only ones showing up will be in this diagonal, and everything else will be 0s.
Would it just keep going like that if you did like 1-by-5, 1-by-6? It would just be keep going
yeah.
ones down.
Right. Yep. If it's a 5-by-5 matrix, it'll just be 1s. Yep.
Okay.
But for our examples, we're really not going to see much beyond these two. It's just, we're not going to be dealing with such messy matrices, especially not by hand. So typically, we're just going to be seeing in terms of just 2-by-2 or 3-by-3 matrices. So here, this example says, if I were to multiply matrices together, if these, let's say this, we have this example here, you got 2-by-2 matrix and 2-by-2 matrix. If these are truly inverses of each other, then I should be able to multiply them together and get a 1, 0, 0, 1 matrix. Okay, let's just see what happens if these are truly inverses of each other. Oh, wait, I'm sorry. Let me back up. That's not what it's saying. This is saying multiplying any matrix by the identity matrix is like multiplying by 1. Okay, sorry, my bad. So let's say I were to multiply 3 times 1. 3 times 1 is equal to 3, right? It's just an example here. If I were to multiply anything by 1, I'm not going to change the value of what I started with. Or if I did 5 times 1, I'm still going to get 5. So what that means is if I were to multiply a matrix by an identity matrix, I should be able to get to where I started from, and my identity matrix is basically just going to be invisible. It's not going to change my value, just like how times 1 is not going to change the 3 and it's not going to change the 5. Okay, so let's test this out. This should take us to, this should leave this second matrix unchanged if I were to multiply a matrix by quote unquote 1. Okay, let's test it out. Okay, so 1 times 6 sorry, I skipped a step here. This is a 2 by 2 matrix followed by a 2 by 2 matrix. We know that our inner dimensions are the same. We're going to end up with a 2 by 2 matrix. Okay, so let's go left to right on the first matrix, top to bottom on the second matrix, 1 times 6, and then 0 times 1. Okay. Second row, first column, 0, 6, 1, 1. One times -2, 0 times -1. 0 times -2, 1 times -1. Okay, so we're left with 6, 1, -2, -1. Yeah, so our initial matrix did not change. We pushed it through, multiply with the identity matrix, we quote unquote multiply by 1. It's not going to change. Okay, so that's another property of identity matrix. It's basically going to it's going to multiply in a way where it's not going to change your original matrix. Right? The reason why is every number not part of the original matrix gets zeroed out, leaving us with the original matrix unchanged. Right? It has a way of not including values that's not part of the original element. Okay, so as part of a preview, I know we're not going to quite get to it. We're running out of time here, but it says find the product of the given matrices to determine if they are inverses. Okay, so we're going to talk about how to get to the inverse in a sec later tomorrow. But right now, the idea is that if I were to multiply two matrices together, if these are truly inverses of each other, I should be able to get a result of 1, 0, 0, 1. Okay, if these are truly inverses of each other. So that's how we're going to determine it. So we're going to do that when we pick up class tomorrow, is when we find the product of two given matrices. If we can show that multiplying matrix A and matrix B will produce a 1, 0, 0, 1, then we can kind of go back and conclude that, okay, these must be inverses of each other because these have a way of canceling each other out to produce this inverse, this identity matrix. Okay, so we'll pick up tomorrow with our notes as well as finishing the 5.02b practice worksheets. We didn't get to 10 and 11, and we'll get to those tomorrow as well. Okay, all right, thanks everyone. See you guys tomorrow.
Bye-bye.
All right, thank you.
Bye, have a good day.
Have a good day, thanks.